Why is Fermion-to-qubit mapping overhead so high? Imagine trying to fit a complex puzzle into a small box. That's similar to what scientists face when translating fermionic systems into qubits for quantum computers. Fermions are particles like electrons in molecules, and they follow special rules called anti-commutation relations. These rules mean their operators don't behave like regular bits or classical particles. When we try to encode these particles into qubits, we need to keep all their unique properties intact. This process isn't simple or straightforward. It involves transforming the mathematical descriptions of fermions into forms that quantum computers can understand, which often requires more qubits and more quantum gates. One big reason for this high overhead is the non-locality of fermionic operators. When mapped onto qubits, these operators act across many qubits at once. For example, a simple fermionic creation or annihilation operator might turn into a long string of Pauli operators, which are the basic operations in quantum computing. These long strings mean the quantum circuit becomes very deep, with many gates, making it harder to run accurately on current hardware. Another challenge is balancing locality and resource use. Some mappings preserve locality better, meaning they keep interactions between particles close together. But these often need extra auxiliary qubits to do so. Others avoid extra qubits but produce highly non-local operators, which again increases the number of gates needed. There's no perfect solution that works well for all types of molecules or systems. The structure of the molecules themselves adds to the difficulty. Molecules have complex interaction patterns, and when translating these into qubits, the limited connectivity of quantum hardware makes it tough. To simulate interactions that are far apart, extra swap gates are needed to move information around, which adds more gates and increases error chances. Finding the best way to order fermionic modes or optimize the mapping is also very hard. Researchers develop algorithms to reduce the number of gates and qubits, but these are still limited by fundamental computational complexity. Even with recent improvements, the problem remains tough. Hardware constraints make things even trickier. Quantum devices have limited qubit connectivity and coherence times. When mapping requires many gates to route information between distant qubits, the circuit becomes longer and more error-prone. In the context of simulating molecules, these overheads mean longer, more complex circuits. This makes it harder to get accurate results before errors pile up. To make quantum simulations practical, scientists are working on hybrid mappings that combine different methods. These aim to cut down on the number of gates and auxiliary qubits needed. Some new approaches also tailor the mappings to specific hardware topologies, reducing the need for extra swap gates. Despite these advances, the overhead remains high because perfectly preserving locality without extra qubits isn't possible for all systems. The antisymmetric nature of fermions forces long operator strings, and hardware limitations mean more gates are needed to implement non-local interactions. So, the challenge of balancing physical accuracy, mathematical constraints, and hardware capabilities keeps the overhead high. This is why making Fermion-to-qubit mapping efficient is such a key hurdle in advancing quantum simulations of molecules and materials.